Hi there everyone, and welcome to another MCAT ACE lecture. And today's lecture is going to start the acid and base chemistry portion. So this is going to be broken down into two separate lectures. The first part will be what's outlined here, and then the second part is going to cover primarily the Henderson-Hasselbalch equation along with titration curves and then a final practice session. So let's take a look at what we're going to talk about today in part one. So we will first define acids and bases. There's multiple ways that we can do this, and we'll talk about the different definitions. We're going to discuss what it means to be amphoteric, which is a term related to acid-base chemistry. And in particular, with relation to being amphoteric, we will have a discussion about water, which is an amphoteric substance. The importance of water, we'll look at the equilibrium for water, which is known as Kw, and the concentration of both the hydronium ion and the hydroxide ion. We'll take a look at pH and pOH, which are the logarithmic transformations for those concentrations. We will discuss strong versus weak bases in a general sense and what classifies something as a strong base versus a weak one. Same with acids. And then we will also take a look at Ka calculations and percent ionization. So that's going to be some acid equilibrium constants. Kb for bases, and then we'll wrap up by talking about diprotic and polyprotic acids and the fact that they can have multiple Kas, and then we will also mention pKa, which is a very common use for referring to acid strength, similar to how we use pH when we're talking about the H+ concentration in solution. So let's get started by defining some different ways that we can talk about acids and bases. So the first of the three major ways we can define this is really the most simplistic, and then it's going to build up in complexity as we move along. So the Arrhenius definition of an acid is going to be anything that can give off H+ in H2O. So by an Arrhenius definition, an acid has to be able to generate positive H+ protons in aqueous solution. And this is key here. It has to be an aqueous solution when we're talking about the Arrhenius definition. And because of that, it tends to be one of the most limiting examples of defining acids and bases. So an example of this would be HCl. HCl is considered a strong acid, meaning it will completely ionize when we put it into solution. And when you put HCl into water, you will generate H+ and Cl-. Now keep in mind that the H+ a lot of times is going to end up as H3O+ as a hydronium ion. Okay, so you may hear me talk about hydronium, which is officially H3O+, and H+ somewhat interchangeably. They're not the same thing, because if I'm in a medium other than water, or I have a different solvent, then H+ may be generated, and I'm not necessarily going to have the hydronium ion present. But usually we're dealing with aqueous acids and bases when we're talking about solutions. So the next thing that I would highlight here is bases. So a base, by the Arrhenius definition, is going to be anything that can generate hydroxide ions in water. And again, in water is key. Okay, so an example of something like this would be the classic sodium hydroxide, which is probably the most common base known throughout the general chemistry courses. So sodium hydroxide, if I were to put it into water, would generate Na+ and the hydroxide ion. So sodium hydroxide, a lot of the other hydroxides that you find mixing with the alkali metals at the beginning of the periodic table, those are going to be your primary bases when you're talking about Arrhenius definition. So then we expand and we go to the Bronsted-Lowry definition. And when we get to Bronsted-Lowry, the acid is somewhat similar, but it does have an expansion. So for the acid, it has to be, an acid by Bronsted-Lowry has to be able to generate H+ in solution. Okay. So to generate H plus in solution, this does not have to be water. This could be any type of solution. So you could have any sort of solvent, maybe like an alcohol or something like that. Okay, and a lot of times people will talk about this. You'll hear the term donor. Okay, so if we're talking about an H plus donor, it's anything that can give off a H plus. Again, the main difference here from the Arrhenius definition is that this does not have to be in water. But other than that, it pretty well holds true to what Arrhenius definition has. Okay, so when we take a look at something like that, an example here, not to reuse HCl, would be H2SO4. Okay. Now, H2SO4 would also meet the Arrhenius definition. However, this is going to meet the Bronsted-Lowry definition as well. So when we get ready to look at a base, for a base, this is where there's really more expansion in the definition here. On the side of the base, it's anything that will accept a H plus. So if something can accept H plus in solution, it is going to be considered a base. Now, this is a very freeing definition compared to Arrhenius, because in the Arrhenius definition, we were forced to stick to hydroxide ions. And when we get to the Bronsted-Lowry, the base is released from having to have a generation of hydroxide ions, and it can be anything that is going to accept H plus in solution. So an example for something like this would be ammonia. So when you have ammonia, you're going to talk about NH3. NH3 does not have any hydroxide ions. So if you generate a acidic proton and it matches up with NH3, you can form NH4 positive. Now when you have this, okay, again, if it's in water, it would generate hydroxide from the water itself. It has the potential to do that, where you can get ammonium hydroxide. However, if water is not present, it is possible that the ammonium ion exists in some other form, okay, than the hydroxide form, and in that case, it still is considered a base. You don't have to have the hydroxide there, right? And then the most expansive definition here is going to be the Lewis. And this one really opens up the definition for the acid. So with the acid, you're going to talk about, in a Lewis definition, anything that is able to donate electrons. I'm sorry, accept electrons. So this is going to be an electron acceptor. And this really opens it up, because now we have gotten rid of the requirement for the donation of a H plus or a proton. As long as something can accept electrons, it will be considered a Lewis acid. And an example of this would be boron trifluoride. This is one of the more common examples they use when they're teaching it in general chemistry. There's a lot of groups that are going to be in the third row of the periodic table, such as aluminum and boron, that can create these sort of complexes with the halides, and they can accept electrons very readily. So this would be an example of a Lewis acid. Now when you get to a Lewis base, it's going to be following the same electron trend. Anything that it would be an electron donor, which is what I originally said. I was thinking of a base there. Okay, so electron donor. And this, if you are familiar with organic chemistry and you've been following along with us, examples of this would be anything that might be something like a nucleophile. Okay, so you could use the NH3 example again. Okay, and in an example like this, the nitrogen could interact with the boron, and the boron would accept the lone pair of electrons, where the nitrogen would donate those electrons, and you could end up with a complex that looks like this. You've got the NH portion. Okay, it gave away some electrons, and then you've got the boron portion here. Okay, the boron accepted. So if something is neutral and then it accepts electrons, it's going to become negative. And if something was neutral and it donated electrons, it is going to be positive. So you would come up with a complex that looks like this, and that would be a Lewis acid and a Lewis base. This is the broadest definition of acid-base that you can have, and it's very important to realize that once you get to Lewis, everything else, so the Bronsted-Lowry, the Arrhenius, those all fall underneath Lewis. Lewis is the broadest category that you can get when you're defining these. All right, so let's talk about what it means to be amphoteric. So put simply, something that is amphoteric has the ability to act as an acid or a base. So if something can act as an acid or a base, it's going to behave according to its environment. So a perfect example of this is water. Water has the ability to act as an acid or as a base. So in the case of something like, let's say that we expose HCl here, okay? If we expose HCl, this is going to become H3O+. So in this case, it accepted an additional hydrogen. So H2O, when you mix it with HCl, was acting as a base. Okay. Now, let's say that I have an example where I'm going to use it with NH3. And with NH3 and H2O, I end up with NH4, okay, plus OH minus. So when I have these two, this time the H2O acted as an acid. And that's because it was the one giving over the additional hydrogen to the NH3 so that this could become NH4+. All right, so if something is amphoteric, it has the ability to act as an acid or a base. It is going to depend on the situation or the environment that that compound finds itself in. Okay, so another brief example of this would be alcohols. So the general class of alcohol, an organic compound, for instance, methanol, okay, because of this OH group right here, it's very similar to water. It has the ability to act as an acid or as a base. And when we get to the diprotic and triprotic acids, you're going to find that after they lose their first acidic proton, they're going to have a conjugate base. And that can act or behave as both an acid or a base, because if it's diprotic, it has another acidic proton it can give away, but it's also already given one away, so by definition, it will be a conjugate base. All right, so let's expand a little bit on water here. And with water, I want to take a look at Kw. So we're going to talk about Ka in a little while, but right now we're going to discuss Kw. So Kw is used when we're talking specifically about water and the equilibrium constant for water. Okay, Kw is the concentration of H plus times the concentration of the hydroxide ion. And this is always going to be set equal to 1 times 10 to the negative 14. And if you see that 14 up there, that's important, because if you know anything about the pH scale, which we'll break into pH in a minute, pH is going to go from 1 to 14 on its scale. And this has something to do with aqueous solutions and water when we're looking at this. So it turns out that when I am looking at water, if the aqueous solution is going to be acidic, it means that there's an increase or a higher level of H plus relative to the OH minus, right? So I would see a lower level of hydroxide in a case like that. Now, if it's going to be a basic solution, right? So for instance, if I dissolve some sodium hydroxide in the water, in that case, I'm going to see a downtick in the H plus concentration. I'm going to see a pickup in the free hydroxide ion. in the concentration. So this should hopefully all make sense based on the definitions we had earlier. And then if you have an equal amount of both, which would be 1 times 10 to the negative 7, then you would have a pH of 7. And true neutral water, by definition, has a pH of 7, which means there's an equal amount, right? When we get to this set here, there's an equal amount of the H plus to the hydroxide. And that makes it neutral. Okay, so where does this pH number come from when we're talking about Kw and these related factors? So when we start dealing with pH, pH is going to be a negative logarithmic transformation of the of the H plus ion, okay, the hydronium ion. So when we take a look at our proton concentration or our acid concentration, we can directly convert it into pH by taking the negative log of the acid concentration. Okay, so what I'm going to do is I'm going to bring up a question here for practice, and we're going to utilize Kw in order to find out the H plus. And when we do that, we can then take a look at how this would relate back into the pH equation. So the problem says ammonia cleaner has 0.003 molarity hydroxide ions. What is the H plus ion value and what is the pH? So what we're going to do in order to figure this out is utilize the Kw equation. We're looking for the H plus concentration, and then once we have that, we will utilize it and find the pH. So if you remember up here, we said that Kw is equal to H plus times the concentration of hydroxide. So that is set to 1 times 10 to the negative 14th, and we can rearrange that equation in order to solve for the H plus. So if I bring that over, so it's what I'm looking for, I can set it equal to Kw over hydroxide. And I know that Kw and hydroxide are going to be 1.0 times 10 to the negative 14th. Okay. And this is going to be 0.0030. Now keep in mind that when you're working through this on the actual MCAT, you would not have a calculator handy. So you need to be able to do rough estimates based on the exponential factors here. Now, if you look down here and you move the decimal over 1, 2, 3, you're talking about an approximate 10 to the negative 3 when you're looking at that. So if you were to take the difference between these, it would be on the magnitude of to the negative 11th to negative 12th, depending on how big it is. So that can give you at least a rough estimate if you're working with it, even though we're going to use the exact numbers here. So if you were to solve this, it's going to equal 3.3 times 10 to the negative 12th. And again, you will not have the calculator. So if you have something like this and then you had to find the pH, what you would need to do is say, I'm taking the negative logarithm of 3.3 times 10 to the negative 12th. Well, when you have something like this, you're really focused on a base 10 transformation. So a little key that'll help is look right up here, and your value is probably going to be one number less than that on a positive scale, somewhere in that region. Okay, so if I take the negative log of 3.3 times 10 to the negative 12th, I could expect a pH of approximately somewhere around 11. Okay, now if you actually plug this in and solve for it, it is 11.48. But again, I'm trying to coach you guys so that you can make some quicker snap decisions if you're facing the time on the MCAT and you need to get through that at a relatively breezy pace so you can keep moving on. All right, so that would be how we are going to convert into pH. Now, if you were interested in going the opposite direction, where you have pH and you're trying to get the H plus concentration, all you have to do is the reverse of the logarithmic transformation, which would be the base 10. So it would be 10 to the negative pH value. So in this example, if I took 10 to the negative 11.48, I should get my 3.3 times 10 to the negative 12th back out of that equation. Okay, so I'm going to go ahead and clear the whiteboard here, and then we're going to just relate pH a little bit more to the base side of things, because pH is normally dealing with acid, how acidic is the solution, and every time that we are discussing acidity and basicity, we're usually discussing solutions in terms of pH. But pH is not the only way that you can describe a solution in terms of acid-base. So let's clear the board and then take a look at that. Okay, so while we know that there is a pH, it's important to realize that there is also a pOH. And that makes sense because if pH is going to be the negative logarithmic transformation of the H plus concentration, I also have a hydroxide concentration. So I should, in theory, be able to take the negative logarithm of the hydroxide, and I end up with pOH. And you can deal with a pOH of a solution instead of a pH of a solution if you would like to discuss how basic a solution is. And again, when we talk about a pH scale, pH and pOH are going to be two different sides of the same coin that are going to equal 14. And that's our pH scale. Now keep in mind, this value, as discussed earlier, is coming directly from kW. So you can put pH and pOH together, and what's useful about this is if you only have access to, let's say, the H plus concentration, but you have a question about the hydroxide concentration, if you can find the pH, then you could find the pOH, which means that you could then access the hydroxide concentration, because then you could also take 10 to the negative pOH, and that is going to give you your hydroxide concentration. Okay, so that's pretty useful because you don't need to know the hydroxide concentration in order to get here. You don't even have to know the pOH. If you can determine the H plus concentration, then you can determine the pH. And if you can determine the pH, you can determine the pOH because it's related through kW. And if you can determine the pOH, then you can determine the hydroxide concentration. So these two, when we're dealing with aqueous solution, are intertwined with one another. As long as you have access to one, you can find access to the other, provided you have some general information at your disposal. Right? So that is a useful way of viewing acidity. It's not just pH, but it's also going to involve pOH on the flip side there. All right, now one of the things that we talked about in our outline is strong acids and bases versus weak acids and bases. So when we talk about something that's going to be strong, we have to kind of clarify here, because strong and weak are going to be relative terms. So the overall idea behind a strong acid or base, okay, so this is going to be considered for both of them. If you have a strong acid or a strong base, it's referring to sources of strong electrolytes. Okay, so if you remember when we talk about solubility and ions dissolving in solution, okay, a strong electrolyte is going to be one that will completely come apart or completely dissociate in solution. And that is what's going to be considered a strong acid or a strong base. So things like, and we've mentioned this earlier, HCl, H2SO4, right? let's see, another one would be nitric acid, HNO3. And then you have things like sodium hydroxide, right? Or your barium hydroxide. When you have things like this, they are considered strong because when you put them into aqueous solution, there is no equilibrium. They go all the way to dissociation. It's not that you have part of it as HCl and part of it as H plus and Cl minus. 100% of it goes over to the H plus and Cl minus side. And because of that, and the fact that there's no equilibrium, that is what defines a strong acid or a strong base in the general sense. Okay? So what does that mean for something that is weak then? Well, a weak acid or base, you may be able to guess based on the definition of a strong one, is going to be any acid or base that will have partial dissociation. Okay, so for instance, when we talk about things like KSP and how, to what extent, or how much something is going to dissociate in solution, this is when we start talking about weak, okay, acids and bases. And weak acids and bases have equilibrium constants because they are partially in the formed state and partially in the dissociated state. And when you have that mix between them and that equilibrium going on, then you're going to have your K values. So you'll have Ka and Kb, just like you can have water with Kw. So an example of a weak acid would be acetic acid, the type that you find in vinegar. So acetic acid, the very basic carboxylic acid, looks like this, and it's going to go into equilibrium in its dissociated form, which would look like the resonance stabilized carboxylate ion. All right, now that setup right here is going to have a Ka associated with it. Now this is just showing the ion. The ion would need to be in the presence of something else when we have the dissociation going on. Okay, so you could have water, and then the water could end up being the thing that generates this anion on the other side here. So keep in mind that whenever we deal with an acid and it goes over to a base, the term that we use for these two are conjugates. Okay? So a conjugate is going to be what's found on the opposite side after protonation or deprotonation occurs. And the way that a conjugate setup works is that if you have something that is considered strong on one side, and then you go to the other side for the conjugate, that's supposed to say CONJ for conjugate, you're going to find something weak. All right, so in an extreme example, take something like HCl. When we have HCl, we know HCl is a strong acid. So if this is going to be a strong acid, I would expect a weak base to result here. Okay, and the weak base that results is a chloride ion, and a chloride ion is by definition a weak base. It is not considered a strong base like a hydroxide ion would be. All right, now that's a perfect example. If I have a hydroxide ion, right, that could come from something like H2O. So when I have H2O, H2O is going to form a hydroxide ion. Is water considered a strong acid? And the answer would be no. Water is most definitely a weak acid, and so it's going to form a strong base as its conjugate. So this is true in the reverse. You can have strong to weak and weak to strong, whether it's acid or base. But you have this conjugate set up. Whenever you have an acid, it has the ability to become a base after it has released that proton, and vice versa. A base has the ability to become a conjugate acid after it accepts a proton. Okay, and that weak-strong relationship will always be in play there. So when we get into a situation where we have acids, the general setup is going to be that you can have something like this. You can have an acid. The acid, let's say, is in aqueous solution. Okay, and it will partially dissociate into H3O plus and A minus. So that would be your conjugate base right there, the A minus. Right? Now, when we get ready to set up the Ka for whatever HA might be, that given acid, you would set it up by saying concentration of H3O plus times the concentration of A minus, because remember it's products over reactants, and then it would be the concentration of HA. Now keep in mind water is a liquid, and water is 10 to the minus 14th, so it's not going to have a large contribution to the Ka factoring. So we exclude water, even though it's present there, when we get ready to calculate the Ka. Now remember that the Arrhenius definition was the only one that required water. So we can have situations where we don't have water present. It's in some other medium, or maybe it's just the acid by itself. Okay, that can go into the H plus and A minus, right? And in a case like that, it's pretty much the same thing. Ka is going to be H plus times the concentration of A minus over HA. Right? So this is just like your other equilibrium constants that you set up. However, it is for an acid. Now, it is important to remember that Kas will only apply for a weak acid. These are only for weak acids. Okay? And the reason for that is K, when we deal with K, is an equilibrium constant, and only weak acids are in equilibrium. Because we just got finished saying how the strong acids completely dissociate. It's one directional, right? We don't end up having this back and forth going on, and so we do not have Kas that are official for something like HCl or H2SO4. We would just say it's got a very large Ka because it's going all the way right into the numerator. None of it would be in the denominator at that point. So that is Ka. Now, what's important to remember is that even when you're among weak acids, you can have stronger weak acids and then weaker weak acids. So that's why I was sort of saying earlier, you have to look at the definition and it's relative as to what's strong and what's weak. So for instance, if I were to take a look at hydrogen fluoride, okay, hydrofluoric acid, the Ka value on this is going to be 7.1 times 10 to the negative fourth. That would be the Ka value that you would get. All right, now if I take the cyanic acid, HCN, this is 4.9 times 10 to the negative 10th. All right, so the gap here is approximately 10 to the 6th. 10 to the 6th is 1 million. All right. So what does that mean? It means that the hydrofluoric acid is approximately 1.5, if you look at the difference between the 7.1 and the 4.9. It's not quite that, but it's about 1.5 million times more acidic. Okay, and that's a big deal. That means that hydrofluoric acid is far more acidic than the HCN is. However, hydrofluoric acid is weak compared to something like HCl, which has complete dissociation. So keep in mind that once we get into weak acids, you're sort of in a sliding scale where you're going to have some weak acids that are the strongest of the bunch, and then they'll decrease from there. And every time you take a factor of 10 and you jump, you're talking about these exponential jumps, right? So something that goes from 10 to the minus fourth to 10 to the minus fifth, you're talking about times 10, and then you jump another one and it's times 100, times 1,000, times 10,000. So you can quickly rack up much more acidity or much less acidity based on those jumps that are there. So what I'm going to do now is bring up another problem that we can look at, and we're going to attempt to solve. So let me put that up here. All right, so this says calculate the pH of a 0.5 molarity hydrofluoric acid solution. So what we're going to need to do here is apply some equilibrium math. So let's first write out the actual equation and what's going on here. We're talking about hydrofluoric acid, aqueous, and that is going to dissociate into H plus aqueous plus F minus aqueous. Okay. Now the best way to solve this is using the ICE method, which stands for initial, change, and then equilibrium. Right? So if you're a little confused with this, you can go look at the solubility lectures and the chemical equilibrium lectures to get a little more information about how we do this type of stuff. But if you're following along, you should be able to gather this. So at first, we're looking at the initial concentration. So hydrofluoric acid, it says right in the problem, is going to have an initial concentration at the very beginning of 0.5 molarity. And we're going to have nothing for the H plus or the F minus, because at the very beginning, when we initiate, it's all in this form, and then it needs time to go into equilibrium before it dissociates to some small extent. Okay, now the change is that I'm going to lose some amount of HF, which we will call X, and I am going to gain that same amount as H plus and as F minus, right? Because every HF molecule is made up of one hydrogen and one fluorine. So when I put those together, they're going to be one of each for each HF molecule that dissociates. So then, just like a math equation, I take a look at what would happen. So I give it time, and then when it establishes itself at equilibrium, I'm going to say this is 0.5 minus X, and then this is going to be X, and this is going to be X right here. So the next thing that I need to do is I need to apply this to the Ka problem or situation. So the Ka, I'm going to just rewrite it down here because you may not remember, but we gave it earlier at the top, was 7.1 times 10 to the negative fourth. So that's the Ka. And we know that Ka is going to be equal to the concentration of the hydrogen, which we said is X, times the concentration of the fluoride ion, which we said is X. And that is going to be over 0.5 minus X. So if you were to solve this, you have to use the Ka value and bring it over all and set it to 0 on this side of the equation. So what you would end up with is something that looks like this. You would have X squared plus 7.1 times 10 to the negative fourth X minus 3.6 times 10 to the minus fourth. All right, now if you have this, what you end up with when you've got something like that is you need to use the quadratic formula. And when the quadratic equation comes up, or the quadratic formula, you have one of two choices. You can go directly into using the quadratic equation where you have to do your x equals negative b plus or minus the square root of b squared minus 4ac over 2a, or you need to then take this, and you are allowed to make a general assumption, but we have to at the end check it to make sure it passes a certain check. Okay, and you should almost always go for the assumption unless there's a really good reason not to. And what we're going to assume here is that X is very, very small. Okay, so what are we saying from a chemical standpoint? X represents H plus and F minus. So what we're saying is because HF is a weak acid, most of it is going to be in this form, which is HF, and there's going to be very little of it in the dissociated form. And we're willing to say it's going to be so little in comparison to 0.5 that we can just go ahead and neglect this. The 0.5 minus X, we're just going to neglect that minus X. Right? So to put this another way, what we are going to say here is that 0.5 0.50 minus x is going to be approximately equivalent to just 0.50. All right? And when you make that assumption, you can rework the equation. So I'm going to, for the sake of room, go ahead and delete this. So just pause it and copy anything down if you need it. And I'm going to delete this so I can continue here. All right, so with that assumption in place, we can now turn around and say that the Ka, 7.1 times 10 to the negative fourth, is going to be equal to x times x, so we'll get an x squared there, but now I can drop the minus x. So it's just going to be 0.5 at the bottom. This becomes much easier to solve mathematically when I don't have to use a quadratic equation. So now I can just solve for x by doing some algebraic rearrangement to begin. So 0.5 is going to be half of this value here. And so that would be 7.1. If you were to take half of that, would be 3.55. And that's times 10 to the negative fourth. All right, and then what you would want to do is take the square root, because this is for x squared right now, and we need to find what just x is going to be. So if I take the square root of this value, then I find x, and the square root of that value turns out to be 0.019 molarity. This is x. And x, if we go back to that original equation, is being substituted for H plus as well as F minus. Now H plus is what we're interested in because the original problem said calculate the pH. So if I want pH, I'm going to need to go ahead and go after the H plus. So since I have H plus at this value here, I can then easily find the pH by taking pH equals negative log of 0.019, and that turns out to be 1.72. So the pH of hydrofluoric solution at 0.5 molarity is 1.72. All right, now keep in mind I said there is an assumption that we're making here, which is that X was very, very small. The H plus concentration was very small relative to the HF concentration. So in order to confirm that, what you need to do is make sure that the ratio, okay, of the H plus to the initial concentration is no greater than plus or minus 5%. So what I want to do is I want to look at this as a ratio, and I would say I have 0.019, and I'd take that over 0.50, and I find out what that would equal. Now you're going to multiply that times 100 because you're looking for a percentage. And if you were to run this, you would get 3.8%. So in this case, we pass that check, and we would be allowed to run with this assumption. If this number goes over 5%, you need to stop with the assumption, and you have to go back and rework the quadratic formula, where you would actually plug all those values into the quadratic formula. And just one more time for people, you probably should know this if you're going into the MCAT by heart, but the quadratic formula, if you want to solve for x, it's going to be x equals negative b plus or minus the square root of b squared minus 4ac over 2a. That's a very important mathematical formula that you want to keep in the back of your head for all sections of the MCAT that would be utilizing math, including chemistry. Okay, so you should note that we had the Ka in this case, but you could also determine the Ka if the pH was given. So we had to use the Ka to get at the pH, but if the pH is given to you and therefore you know the concentration of the H+, you could work backwards and you could determine the Ka as well. That's also a possibility. Okay? Now sometimes you will find that questions or statements are referring to percent ionization. And percent ionization is going to be looking at how much is actually in the H plus form relative to the initial concentration. So this check right here is a percent ionization check. And what we're looking at is the H plus at equilibrium over the initial concentration of HA. Now, in this case, it was HF, but we're saying HA for a generic acid. This formula is the percent ionization. So if you ever hear somebody referring to percent ionization, this is what they're looking at. And obviously, the higher the percent ionization is, it means the more of the H plus is in that free form, right? Because the numerator is getting higher in that case. Now, we're using it as a fail-safe check in this specific instance, but some people just report the strength of an acid as percent ionization. So let's say that this was something like 81%. You would have to go back and use the quadratic formula to really solve for X. And then when you find X, you would then take that value of X, put it over the initial concentration of HA and solve for that, and that would be your percent ionization in a case like that. So we're going to try to wrap up here in just a minute. So I'm going to go ahead and clear the board. We will discuss the last couple of things that we need to, and then we will wrap up here. And make sure that you tune in for part 2 of this lecture, where we will get more into the Henderson-Hasselbalch. We will also take a detailed look at titration curves. So let me clear, and then we will finish this up. Alright, so getting close to the end here, the next thing that we want to talk about is diprotic and polyprotic acids. Okay, so when we start talking about these are going to be acids that have more than one acidic proton available for removal. So you could be talking about things like H2SO4, there's 2 of them. When you deal with phosphoric acid, H3PO4. Right? Or something like carbonic acid. These are all examples where you have more than one acidic proton that can be removed from this set. And when you have more than one acidic proton, every acidic proton is going to have a Ka associated with it. So what you get into is a situation where you have multiple Kas, and you have to look at the equation for each specific one that you come across. So, for instance, let's take a look at carbonic acid. When we have carbonic acid, the initial reaction that we would have is H2CO3 aqueous, and this could dissociate into H plus aqueous and HCO3 minus aqueous. Okay. So when you have this, you would have a Ka, and this would be referred to as Ka1 because there's going to be a Ka2. So Ka1 would be H plus times the HCO3, which is going to be your conjugate base. That's the equivalent of A minus when we're looking at the generic formula. And then that would be over H2CO3. Right? Now, you would have a Ka2 because once you get to that point, you could also have the conjugate base is amphoteric in this case. It could also act as an acid. So we could take this carbonate ion to bicarbonate with that H on there, and that could give up its H plus, and then you would end up with CO3 2 minus. So in this case, you're going to have a Ka2, and the Ka2 is going to be H plus CO3 2 minus, and that would be over what is now considered the new acid, HCO3 minus. Now, an important concept to keep in mind when you're dealing with diprotic and polyprotics is that the first proton is always going to be the easiest to remove. They will get more and more difficult, or they will become less and less acidic as you continually remove them. And that's because if they started off like this, they're becoming a conjugate base. So you are then attempting to take a proton off of a base. Bases like to accept protons. So each subsequent one will be more difficult than the one before it. So in this specific case, the Ka value for Ka1 is 4.2 times 10 to the negative 7th. Whereas in case 2 here, when we have Ka2, it is 4.8 times 10 to the negative 11th. So if you look at the difference here, it's an approximate difference of 10 to the 4th. And when you have 10 to the 4th, that is 10,000. So it's saying that it is 10,000 times more difficult, or the proton is 10,000 times less acidic in that second removal process when you get to the HCO3. Okay? So keep that in mind when we're dealing with diprotic and polyprotic acids. And you will also see in titration curves, now we're primarily going to talk about this in the second lecture, but when you see this, you will see a titration curve, you'll see one proton gets removed and then it levels, and then you may see another proton that gets removed and it levels. Something of this nature, because you'll have multiple Ka spots where you have a deprotonation, it levels off, and then you have another deprotonation as more base builds up in solution trying to remove that second acidic proton. All right, and speaking of bases, it's important to keep in mind that we've been talking about Ka all this time, similar to how we talk about pH very often. But just like with pH, there was a pOH, there is also a Kb. So there's not just Ka, but you can also look at the equilibrium constant for a base. So Kb exists, and we could have something like NH3, which we classified as a base at the beginning of this lecture, okay, plus H2O. Remember, H2O is going to drop out as a liquid. And we get the NH4 in the example that we used, and the hydroxide. All right, so this is most definitely a base. And when we get ready to look at Kb, you would set it up the same way as Ka. However, Kb is going to be looking at the base. So it's NH4 plus, right? And it's OH minus. So remember that in the Ka, you're looking at the H plus. Here you're looking at the OH minus and the conjugate, whereas in the Ka example, you're looking at the H plus and the conjugate. Right? And this is a conjugate acid, obviously, because we're dealing with Kb. Whereas in Ka, we're dealing with a conjugate base. And then you're looking at the original base down here, which would be NH3. Okay? So that would be an example of Kb. Now this can be used to find hydroxide. But again, remember, if you can find the H+, then you could also find the hydroxide via Kw or POH when you're dealing with that. But this is a way that you could find the hydroxide if you have Kb and you want to work with that. So the last thing we're going to do, just to wrap up here very briefly, and this is going to, we'll probably recap this at the beginning of the next lecture because it builds into the Henderson-Hasselbalch equation. We're going to talk about pKa briefly. All right? So similar to pH, pKa is going to be the negative logarithmic transformation of a Ka value. So we have these Ka values, they're usually to the negative some exponent, and when we have them, you can plug them into a negative logarithmic transformation, you get pKa. So just like when you have the small H plus concentration, you plug that into the negative log, you get the pH. If you do it with Ka instead of H plus concentration, you get a pKa value. Now pKa values are very common when you're using everyday acidity talk. So just like when you're talking about the pH of a solution, most people, when they talk about solutions, they say this solution or this buffer is at a pH of 2.2, right? They don't say it's at a concentration of, 3.2 times 10 to the negative 5th ions. So similar to that, most people do not go around talking about the Ka of an acid. They talk about the pKa of an acid. It's a smaller, more condensed number that's easy to use, similar to pH. Okay? So the important relationship here is that the stronger acids have low pKa's and they have high Ka's. So these have an inverse relationship to one another. So in other words, the larger a Ka is, the smaller the pKa is going to be. Okay? And that makes sense when you think about it, because something that has a large amount of H+, that means there's a lot of acidity in it. You would expect a low pH number, right? So what do we think something really acidic? A pH of maybe 1 to 3. That means that the concentration that leads to that pH is going to be very, very high. We need a high amount of H+ in solution to get that level of pH. And so the same thing is true here. We need, okay, a very large Ka value in order to get low pKa values. And low pKa values mean that we have strong acids. All right, so that wraps up the first lecture on acid-base chemistry. We've talked about ways to define Arrhenius, the Bronsted-Lowry, and the Lewis. We talked about being amphoteric, which means you can have either an acid or a base behavior, depending on the solution and the situation you're in. We talked about water, Kw, right, 10 to the minus 14th. And H+ and OH- and how they play into that. We also talked about pH and pOH and related those to the concentration of the H+ and the hydroxide ion. We talked about strong versus weak and ionization. We did Ka and discussed calculations. We did one of the equilibrium ice concentration calculations. We talked about percent ionization and the check when you are ditching or making the assumption to ditch the quadratic formula. We then talked about Kb and bases along with diprotic and polyprotic acids, and then we wrapped up with pKa. So in the next lecture, we're going to take pKa and we'll start off by really showing you the Henderson-Hasselbalch equation, maybe talking about buffers a little bit, and then we will bring in the titration curves and sort of look at equivalence points, indicators, and pKa and Henderson-Hasselbalch in relation to some of those titration curves. So that's going to wrap it up for this lecture in part 1. So this is for MCAT ACE, and I will see everybody in the acid and base chemistry part 2 lecture, and we will see you there.